Hello, this is Mrs. Hanson again. I apologize for video number 2 ending rather abruptly. Let's just say I did pull out my credit card and upgrade Screencastify so that if it goes like 10 minutes in like 2 seconds, it won't cut me off. So hopefully that won't be a problem again. However, just to make sure my handwriting was so bad, I went ahead and just typed some more thorough answers if you want to read through them. But just to summarize that last one. So if you had UV light instead of violet, which is a more energetic photon, those the same intensity, you are going to have the same number of photons, and it's one photon per one electron. But since UV photons are more energetic, you're going to eject the same number of electrons. But what do you do with the extra energy when each one of those photons kind of pop? Okay, you're going to use what energy you need to eject the electron, but then with the extra energy in that little photon, it's just going to propel each electron with a little extra kinetic energy. Okay, so we'll close up that conversation, but then there were some calculations that went along with it. As always, I hope that you work through these calculations and then pause the video and then come back and check your answers. This is photoelectric effect, but it's a little different because we're seeing how much energy would a photon have to be to break a bond in an ozone molecule, which is O3. So kind of like it's one photon per one electron ejected off the plate. Here, it's one photon to break one OO bond. Okay, so it says a molecule of O3 absorbs a photon with a frequency that's given here. Okay, so the first question is, oh, well, how much energy is in that photon? Okay, so that being said, that's pretty easy. We're going back to those formulas we used earlier. Okay, and sorry about the random lines on the screen. E equals Planck's constant times the frequency. Now, do keep in mind this is the energy per photon. So Planck's constant times the frequency, and we got this very small joule value because it's just per one photon. Now, this next question is interesting. It says, oh, well, the minimum energy needed to break an ozone bond is 387 kilojoules per mole. So that means per mole of OO bonds. Okay. Does this photon with the frequency that we were talking about earlier, is it energetic enough to get the job done? Okay. So basically, we're going to take this number and work with that and do sort of a comparison. But as this says, this is based on a mole of those bonds being broken. So I went ahead and said, well, okay, I guess I'm going to need a mole of photons here. Okay. And for every one photon, as I calculated earlier, it would have 6.63 times 10 to the 19th joules. Convert that to kJs, and if I had a mole of these photons, then I'd have 390 kJs. Is that enough to break these bonds? Well, 399 is greater than 387, so that means I would have enough energy with each one of these photons to break a mole of those OO bonds in ozone. Okay. Now, there's other ways you guys could do this problem. You could have certainly taken this number, the 387, converted that to joules, divided that by 6.02 times 10 to the 23rd to say, oh, well, this is the energy that would be needed per photon. Compared it to this number, and again, I think you would find that yes, you do this. These particular photons would be energetic enough to break OO bonds. Okay, so that's photoelectric effect, but kind of applied in a different way with breaking bonds. Okay, all right. So where is this all going? Well, this little graphic is the one from class, and we'll get to that later. We talked about de Broglie's formula, so the fact that light has wave-like and particle-like behavior, and also matter has wave-like and particle-like behavior. So hopefully we're kind of putting all this together. Eek! These things we'll probably show you in class, but those are just what you can do with electron microscopes because electrons have distinct wavelengths. They can kind of bounce over surfaces and fit through gaps in crystals, for instance, and you can get these really cool images. But we'll talk about that later. Okay, so now where do we go with all this stuff? So this is a review from definitely regular chemistry. So hopefully this will jog your memory. Okay. Going back to light, there's continuous spectra and line spectra. Continuous spectra is when all wavelengths of visible light are represented. So basically, this is white light, okay, or sunlight. So those are some great examples. Okay. So any white light you see is just a blend of all the different wavelengths of the visible spectrum. Now, line spectra, that's way more important to what we talk about in chemistry, is when only specific wavelengths are emitted. Okay, and you guys probably remember last year you did a lab where you took the diffraction gratings and you looked at elements and the light they were producing. And what you saw is that every element produced unique line spectra. So I don't care which two you pick, but why don't you pick two, maybe helium, maybe neon, and just transfer those to your notes. Okay, but what I want you guys to see here is that each one of these elements has a very distinct and very unique line spectra. All right, so good, good. Hopefully you drew two. So, but the question is what's really going on here? So, if you guys remember from last year with those electricity tubes, the element was in a gaseous form, and basically electricity passed through and excited the electrons. Okay, and the electrons, they didn't like being excited, so when they fell back down, energy was released in the visible range at very distinct wavelengths. Okay, we'll probably watch this little simulation in class, so we'll come back to that. All right, and then another way you guys could see that is we looked at the element tubes, but then we also did flame tests, and you guys did this lab last year too. So that's just when you see the line spectra, but all those wavelengths blend together to produce one distinct color. So here's the fun part. These are some distinct colors that are produced by these distinct compounds, and you guys can try to match them. Okay, and if you guys remember one thing from last year's experiment is that it was always the metals that their electrons got excited, and when they fell back down, they happened to produce wavelengths in the visible region. So, nitrate and chlorine and the nonmetals, of course, their electrons get excited too, and they fall back down, but they're just not typically in the visible range. They might be in the UV sometimes, or they might be in the infrared. All right, so do you guys remember which one this beautiful green color is? Because this is our best representation of Mason green. Copper produces that distinct green. Potassium, that's this beautiful lavender that you guys might remember from last year. It's kind of hard to see that one. Lithium and strontium are my two favorites because they're these beautiful red orangey colors. Lithium is definitely your hot pink, and strontium more of sort of a deep orangey red, I would say. And your sodium chloride, just like that lamplight we talked about in the earlier example, is that distinct yellow. Okay, and this one, boy, I don't know what that one is. I'll have to think about that. Might be boric acid. So anyway, bottom line is that these elements, all of them produce these really unique colors because they have unique line spectra. Okay. All right. But what we really want to get at is why do we create those line spectra? So it has to do with Bohr's model. So keep in mind the nucleus right there in the center, and these are the energy levels. So first energy level, second energy level, third energy level, and so on. So, according to Niels Bohr, a single electron in a hydrogen atom could be located in only certain energy levels. So, the bottom line is you got to have an electron here, you can have an electron here, but you can't have an electron like in the middle. Okay. As you go further away from the nucleus, the energy of each energy level increases. So, the closest to the nucleus, that's called the ground state, and the further away you go, more energetic, more energy. So n equals 1, it's the first energy level, represents the lowest and most stable energy level. And as I just mentioned, we call that the ground state. And greater than 1 represents less stable or more unstable energy levels or excited states. Okay? So here's kind of a worded description of how we create the line spectra of the flame test. So hydrogen's electrons prefer to hang out in their ground state. However, if given enough energy, the electron can jump to a higher energy level. Okay, so here's my electron, can jump to a higher energy level. Okay, electrons don't like being in the excited energy level. And by the way, this would be, you'd have to put in energy to excite the electron, either with fire for the flame tests or electricity. Electrons don't like being in the excited energy level, so the hydrogen electron will fall back down. Fall back down. Okay, and when that happens, it's going to go down to a lower energy level. A photon of light or electromagnetic radiation is released. All right, so then coming out of this will be some kind of photon. All right, and of course, the real fun part is we're in AP chemistry. So we can actually calculate the energy of the photon that would be released there. Okay, and I'm sure you guys can guess. The greater the drop, the more energetic the photon. All right, so we have this formula, okay, and let me be clear that this only this particular formula only works for hydrogen, okay, and I've seen some books that might go through energy transitions with helium, and usually that's about it, because then it gets pretty difficult to do these calculations or see the patterns. But for hydrogen, the simplest element we have, basically the energy of an electron in a particular energy level, let's say n equals 4, n equals 3, okay, is basically Rydberg's constant, okay, which is only true for hydrogen, divided by n squared, the energy level squared. So it's a pretty easy formula, okay, and but we really don't care about the energy of an electron in an energy level, but rather the energy difference, because that's what's going to be emitted as a photon, okay? So if we keep going, I think there's an example here. Yes, it's coming. Okay, so we'll do the conceptual approach first, some questions, and then we'll do some math with that. So here's basically the energy levels again. And please notice that if the nucleus is right here, what's happening to the energy levels? So there's quite a lot of distance between N1 and N2, a little less distance, a little less distance, a little less. And that's really how the energy levels are arranged. Okay, so we get used to seeing Bohr's model of the simple atom like this, where there's equidistance. That's not really the case. So please remember that the energy levels do get closer together or more closer in energy the further you go from the nucleus. So it says which energy transition would produce a photon of the greatest energy. Okay, now remember, if it's producing a photon, is A on the table? No, because the only way that A is going to happen is if you apply or put in some energy so that you can excite the electron. Okay, so if we look at B, C, and D, greatest energy would be the greatest drop. So that looks to me like that's going to be letter C. Okay, so we're dropping all the way from n equals 6 down to n equals 2. Greatest transition means the greatest energy. Which energy transition would produce a photon of the longest wavelength? Please remember your 3 L's. That longest wavelength means low energy. So that's actually going to be the shortest transition. So we would be looking at D for that one. And last but not least, if transition B was a wave of blue, okay, then transition C, would it be purple or green? Well, C is a bigger energy transition, so it's going to have to be a more energetic color. So thinking about Roy G. Biv, what's more energetic than B? Well, that would have to be our purple, okay? So a more energetic photon. All right. And then, like I said, I promised you guys a little math. And as always, I would suggest that you work through this and then check your answers. So pause, work through it, come back. But this time we are going from transition C, which transition C is going from n equals 5 down to n equals 2. Okay? If you take a look, you can calculate the energy of the electron and ooh, was that 6? Yes, it was. Sorry. So n equals 6. There we go. You can calculate the energy of that electron in the 6th energy level by using Rydberg's formula. Okay, and then you can do the same thing for the 2nd, and you can just subtract those. Now, notice that honestly, it just really doesn't matter how you subtract these. The bottom line is that it's going to be energy released. So you really should have a negative number, okay, to show that it's like exothermic released. However, as we well know, you can't really have negative energy. So we end up dropping that negative anyway when we go ahead and calculate the wavelength, okay? So pop that into one way or another, a lot of different ways to solve this, but however you want to go from energy to wavelength, okay? And life is good. So once you get that wavelength, it's going to be in meters. You can convert it to nanometers. And just like we predicted, that was going to be in the purplish region of the electromagnetic spectra, okay? All right. I think that's it. Don't forget that you definitely need to square these. You, I don't know. There's something funny you guys sometimes do with the math, and just make sure that you do square these before you can do the subtraction. Okay. All right. So what do you think? Pretty easy, right? And of course, this formula would always be given to you. All right, last but not least. Actually, that is the end. So thank you so much for listening, and you get an A plus 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 for the day. Yay! Have a great day.